Okay, this video is going to be a little bit more about using these equations for center of mass and also figuring out what happens when we have solid objects. So remember that we have our definition for center of mass is going to be 1 divided by the sum of the masses, and then times the first mass times its x position, second mass times its x position, and so on. We can group all this together and say that center of mass is 1 over the total mass, and we're going to add up. I think we want to have I equals 1 to n or something like that of mi times xi. And what this really means is if we have some sort of coordinate system here and you've got different masses at different places, mass 1, mass 2, mass 3, mass 4, each mass is going to have its own x position, x1, and then oops, all the way over there to x2, all the way over there to x3, all the way over there to x4, and so on, that you can find the center of mass of this system by doing this, summing them and adding m1, x1, m2, x2, m3, x3, and so on. If we want to, hey Phoebe, Phoebe's right here. I need you to keep your hand away. There's sometimes what we can do is we can assume some things about some situations. So let's say I've got a stick that looks like this, and this is one of your problems in the book, another stick that looks like this, and another stick that looks like this. And I want to find the center of mass of this system. So let's define a couple things here. Let's call this M1, and this M2, and this M3. So I want to find the center of mass, and I'm knowing it's going to be like around here somewhere. What I can do is set up a coordinate system that makes things pretty easy. So let's set up our coordinate system like this. So here's x and here's y. Maybe we'll even make y going positive in this direction. So I know in the x direction it's going to be right in the center right here. Assuming, I should say some things. First of all, let's say that m2 equals m3. That's one thing I really wanted to say, so that this mass right here is the same as this mass right here. That means I know my center of mass is in the x direction. It's along this axis somewhere right here, if m2 equals m3 and m1 is uniform. So what I want to figure out is what's the y position. In order to figure that out, what I can do is I can assume that this whole thing of m1 is like one particle that's right in the center. So I can translate this into, here's my axes again, here's x, and y I'm going to make going this way. So I can make one particle here, m1, like that, and then I can make another particle for m2 right in its center, which is going to be about right there, m2, and then another one for m3, just like that. And then if I'm trying to find the y position of the center of mass, the y center mass position is going to be 1 over m1 plus m2 plus m3 times m2 and whatever this y position is right here. We'll just call that y2, and we'll call that y3. And by the way, m1 has a y position of 0, so I can do m1 times 0 plus m2 times y2 plus m3 times y3, and so on. And that would give me my y position of my center of mass. And then, I could simplify this a little bit. If m2 and m3 are the same and y2 and y3 are the same, I can find it a little more easily. And then it's going to be, somewhere in this area will be your center of mass of that system. So that's one thing to do. Another thing to note is there's another problem where you have a chunk taken out of something. So let's say I think it's just an example problem in the book where they use a circle. Let's say I have a solid rectangle, and I want to take a chunk out of this rectangle just like this. So we'll take a square chunk out of this, maybe even it's a square. What's interesting about this is I can say call this whole piece over here M1, and then this little chunk over here I can sort of call it like M2, but this is a chunk I've taken out of it. So it's really like minus M2. I've taken something out of it. Let's say M1 was maybe the mass of the whole thing, and M2 is the mass of the chunk that got taken out. So I can figure out, if I set up a coordinate system again, let's say I set up a coordinate system like this, y and x. As long as things are uniform in the y direction, excuse me, I'm going to have my center of mass is going to be along this axis, and I want to find the x position of the center of mass. So what can I do? Interestingly enough, I can say that this is adding up the masses, m1 plus minus m2. Remember, m1 is the mass of the entire thing, and m2 is the mass of the chunk that you got taken out. Then I multiply this by m1 times x1, and I want to add in minus m2 times x2. So it's like I'm adding in the negative value of this one. And of course, what that can look like is 1 over m1 minus m2 times m1 x1 minus m2 x2. So it's like a negative center of mass, or a negative amount of mass, if you want to think about it that way. So when you pull a mass out, you can subtract out that center of mass part right there. Okay, great. So that's one thing. I want to now actually take a look at this and then change that into what happens when we have something uniform. So let's switch over here. We'll just write that down again. XCOM is 1 over m times the sum from I equals 1 to n of mixi. What I'd like to do is to be able to figure out, of course this works if you have a bunch of particles, as we said before. You've got a thing, a thing, a thing, a thing, a thing, a thing, a thing. So I want to see what happens when this turns into a continuous uniform density system of particles. So rather than having m1, m2, m3, m4, what I'm going to have is I'm going to have a whole bunch of little bit of tiny bits of mass right here. So these tiny little bits of mass are going to be dm's, a little bit of mass, and we're going to have to add up all these little bits of mass. So when we do that over here, of course, when we have infinitesimally small pieces, we're going to end up with integrals instead. So we're going to have 1 over big M, and it's going to be the integral. And this time it's going to be dm, and we're still going to have an x value for that dm, so we're still going to be how far away from our origin is that little bit of dm. So this is going to be x dm. And then we can integrate over this entire thing and figure out where the center of mass is. Of course, if I have a uniform density, say stick, I know the center of mass is going to be in the middle. But what I'd like to do is figure out how do we use this to prove that the center of mass of a, say, a uniform stick is right in the middle. So I want to take you through that process right now to figure out how we know that this is going to be right in the middle. Okay, so how do we do that? First of all, I want to introduce some concepts here. The concepts are going to be about density. Usually the way that we think of density is how much mass per volume something has. It turns out that that's actually one of the types of density that there are. And there's 3 different types of density, or maybe even an infinite, but in our 3-dimensional world, we usually have 3 different types of density. So this one is going to be volume density, and this one is going to have a symbol of rho, like that, and it's going to be mass per volume. And the units for that would be kilograms per meter cubed. You can also actually have a area density. So you could have a mass per area, and that says mass, not Mars, a mass per area, and that is, well, I should back up a little bit. If you have a solid object, then it's going to have a mass per volume density. If you have a 2-dimensional object, say just like a sheet like this, then it's going to have a mass per area. That's going to have a symbol of sigma, and that's going to be mass per area like that. And then the units are going to be kilograms per meter squared. So if you have a 2-dimensional object, of course you can also have a 1-dimensional object. So the third kind of density we can have down here is going to be mass per, what do you think it's going to be? It's going to be length. Mass per length. That's going to have a symbol of lambda, I guess, for length. And then that's going to be m over L. The units for that are going to be kilograms per meter. Right, so that's mass per length. So we're going to actually do this problem up here to try to figure out what is the center of mass of a uniform stick. I'm going to make that uniform stick actually just 1-dimensional. So it's just as going back and forth like this. We could expand it to 2 and 3 dimensions. So we're going to be dealing with this. So why do we have to do this? Well, if we look back up in this formula right here, it's very hard to integrate x and dm because these are different variables, and the x is going to depend on the dm is going to depend on the x, but you can't just integrate like this because I don't have the variables aren't the same. So I have to figure out a way to express dm in terms of x, in terms of something else. And the way we're going to do that is to realize that if we're talking about this stick up here, this little bit of mass right here is going to take a little bit of space. So it's going to have a little bit of space that's going to take up right here, which is going to be a little bit of dx. Phoebe, keep your hands away. Great. So it's going to take up a little bit of dx right here. So this little bit of mass takes up a tiny, tiny, tiny little bit of space right here. What that means is we can actually express dm over dx, which is a mass per length. This is actually going to be our same length density, right here, which of course is going to be the same as the mass per length. If this thing is a uniform density, if you cut it into smaller pieces, each of those pieces still has the same density as the original piece. So a little bit of mass over a little bit of distance is going to have the same as the full mass over the full distance. So that what I can do now is, I'm going to write that down here, dm dx equals lambda. So I'm going to change that into saying that dm is going to be lambda times dx. So that's going to allow us over here to now change this around. So let's set up the problem. We're going to have a one-dimensional stick, and it's going to have a length of L from one side to the other side. It's going to have a mass, it's going to be m, and it's going to have a linear density of m over L. And we want to find out where's the center of mass. So we're going to set up our coordinate system just like this. Here's the y-axis, and then there's the x-axis underneath it. We want to figure out where's the center of mass. Of course, we know it's going to be L over 2, but let's just figure it out using this formula, this one right here. So we're going to have x center of mass is going to be 1 over the mass times the integral of x, and now dm is going to be over here, is going to be lambda dx. Lambda dx. The lambda is a constant, so we can actually pull that one out. So it's going to be lambda over m times the integral of x dx. I forgot to put limits on the integral. We're going to integrate from 0 to L. From 0 to L. Now this is an integral you can do. X dx, that's pretty easy. Let's start it back over here. So we're going to get lambda over m, and when we integrate x dx, we're going to get 1/2 x squared. We're going to want to evaluate that from 0 to L, just like that. So we're going to get lambda over m, and plugging in L, 1/2 L squared minus, plugging in 0, 0, just like that. All right, here, let's come around over here. So we're going to get lambda over m times 1/2 L squared. It's like, wait a minute, L squared? We were expecting L over 2. Let's figure out what's going on. What's going to happen is we're going to substitute back in for lambda is going to be m over L. So this is m over L over here. So this is going to turn into m over L over m times 1/2 L squared. M is going to cancel. One of those L's is going to cancel. And guess what? This ends up as L over 2. Which is what we were expecting, right? We're expecting it to be right in the very center. So this is actually a really powerful way to look at things. When we get to talking in our next unit, when we talk about moment of inertia, we're going to do some integrals similar to this. So you can see how it'd be easy to expand from here into a two-dimensional situation and into a three-dimensional situation. And maybe we'll try out some problems like that. Okay, hopefully that helps you, and have at it with the problems in the book. Actually, I should say that none of the problems in the book are going to be integrals. This was just something special we were doing right here. So all the problems in the book are much more straightforward.